Welcome to this video, and let me continue from our previous discussion about our CAD exercise 9. It will be about ENOB verification, effective number of bits for ADC. So for the first step will be the baseline ENOB without noise. So we will verify as a baseline how to verify our ideal ADC using Verilog A model. So for that kind of model, if you cannot find this AHDL library from your environment, you have to add it by adding this the path, or in other universities it will be different. But basically it can be found under the FII path. So for ADC, you can import this ADC going through here and then search by ADC, for example, 8-bit idea, and the clicking symbol, then I think we can edit here like this, and this is exactly same as this one, and this one is either 8-bit DAC. So this is already built in. You can find it Verilog A script by opening it. It's quite, I believe, will be quite straightforward if you can go through it one line by line. It is about just approximated, successive approximation ADC, which is a star ADC. Anyway, you can just simply just think about it. This one is just ideal ADC model. So for the ADC setup, we can set like this. For example, rise time, forward time, just 1 nanosec as a very good starting point. You can of course set it as a 1 picosec, is fine. But 1 microsec is sometimes a bit challenging to model the real environment. So what I typically suggest is to just set it as 1 nanosec. And for the delay time, so this one is representing as a ADC's quantization latency. So as we have seen, this is the typical waveform of sample and hold, and so on and so forth. So track and hold. So this period is a track and hold. This period, track and hold. So within this hold period, we happen to process our sample data by doing the quantization. So let's say our quantization happens. Our quantization is completed after some delay. So there should be some delay. It cannot be processed by instant within 0 second latency. No, this is not physically possible because this our circuit is physical circuit. There should be some delay for processing our quantization step. So we can model as a simple approach as 0.25. So this one is a whole period, so 100% period, and this part is 25%, right? So this is quite similar what I modeled in previous video, like such as 0.75 over TS as a delay time or settling time. So anyway, you can follow this approach, delay. I will show how the waveform look like. And for the logic high, if your VDD is 1 volt, you can assign 1 volt. If your VDD is 0.5 volt, you can assign it. And this one is half a VDD. And everything else is similar as a VDD or ADC setup. And for the DAC part, it is even more simpler. Like reference voltage as the same as VDD, delay time. Here, you don't need to worry about delay time. So we are trying to verify our ADC. So this DAC is intended for easier FFT. So let's assume that we don't have DAC. Then we have to plot every single every single wire, and then add them up. Of course, we have to assign binary weight to the power 7 and so on and so forth to to the power of 2 plus, times, and so on and so forth. So it's quite inconvenient. For the sake of simplicity, we can add it as a DAC, such that we can only plot this one, or click this one, and then plot it and run FFT to verify whether our ADC is working correctly or not. Okay, so for that reason, well, for delay time, we don't need it, because as soon as our digital data is converted, well, we can just simply follow, as an analog value, like this. So for just verification purpose, we don't need delay time. Rise time, fall time, is fine. And trends, this is a transition threshold. So you can just set it as a half VDD. And for just a small tip is that if you press Shift, you can automatically assign some net name. For example, here, not Shift, space. And you can also press space. Then you can do this way. And if I save it, that is assigned this way. And if you erase all of this, then for example, let me do this this way then. Yeah. For example, this is still fine, but if you want to plot it as a data binary bus, like this is a cadence virtuoso convention. But if you run some digital domain Verilog simulations, it should be like this way. But this is a Verilog convention. This one is a cadence virtuoso convention. I don't know why this is so different, but it's just as it is, so we have to follow it. Anyway, so to plot the digital data, it should be, we have to follow the convention of how our digital bits are represented. So if you press L, then you can add label. So let's assign the data as like this way. And then at this point, you can press tab. Then you can see, I cannot see it in this environment, but if you click like this, then you can assign a label to the wire. For example, here, then kind of this wire is assigned with label. Let me see if I click net highlighting, and this one is, I think it's not well assigned. So what I want to say is that, let me see. Oh, how can I remove our props? Okay. So what I want to say is that if you set as like this and then press tab once and then expand bus names, then what you can do is that you can click this one, then you can find it, right? So it immediately switches from 7 to 6. So if you click this one, you can assign 6, the bit level 6. How do I say? The sixth position of, no, it's the seventh position of your bit location, and click 1 by 1. And you can assign the bus names this way. It's very easier. So if you don't, let's move it. So if you don't enable this expand bus names, then only you can do is just this way. Of course, this doesn't make sense because this VD0 individual wire only means that we are assigning only 1 bit per each bus. Doesn't imply or doesn't represent what we want to express as sort of land names. And it's also important to notice that its bit order is flipped here. What is laggy? So what I mean is, so here is a 7th bit. So this one is MSB, most significant bit. So you have to select this one as the first bit. I mean the highest bit location, and you can move the other way. So this way. So such that D0 corresponds to VD0, VD0, D1 corresponds to VD1, VD1, and so on and so forth. Okay, and set up clock and clock bar. Here, the clock of this ADC is clock bar because we involve sample and hold or track and hold circuit, which is sampler, as I said. So let's first draw this segment of signal. Then let's say this is a sampler. Then track, hold, track, hold. This one is track and this one is hold. So the first half period here, this one is when clock is 1. And for the hold period, clock is 0. And our ADC wants to quantize within this region. Of course, you can use ADC without sampler. This is also fine. You can connect this one as in. But in real ADC modeling, for example, if we want to design our ADC using our designed sampler and then add like quantizer, then step-wise, it is better to model quantizer altogether with our designed sampler. So for the sake of modeling purpose, you can plug clock bar because our quantization happens when clock is 0. And for the rest of the circuits, it is same as bootstrap sampling switch, input, and the output of the sampling switch. And you can assign 250 femtoperiod. Okay. Sampling capacitor. And now we can build a simulation setup. Let's go to ADEL and copy from cell view. So for amplitude in, because this one is a single-ended, you can assign 0.5 such that its peak to peak is 1 volt, peak to peak, and DC offset is 0.5. And for bootstrapping CAD, we confirmed that 200 femtofarad was good enough, and clock 1 megahertz. And input frequency, now you can reuse. So for example, as you have gone through, load coherent samp. .il. Okay, then it's a skill script. And coherent samp, our input frequency is 490 kilohertz, and sampling frequency is 1 megahertz. And the number of samples, well, we can start, for example, from, let's say, 2 to the power of 8. Here, 2 to the power of 8. Then you can use this value, paste, and edit. So let's set an FFT to the power of 8. And for the simulation time, you can assign T-trend such that an FFT over clock plus T settle. And for the T settle, at this point, well, I'm not sure how big its value should be. So let's start from 0. Yeah, so let's first run it. Let me see. It's all right. So problem is solved. Took me for a while. So anyway, so the first thing you can try is that removing this Aalto simulations, which is your simulation dumped files are existing. And the second one is running this one, switching different caliber version. And then that's virtual. So using removing this simulation folder and using this different caliber version, this corresponds to only for Aalto University student. Yeah, because other universities may have a different environment, so I cannot guarantee whether this method can solve the problem. Okay, so let me go back to this simulation setup. Let me see. Okay. All right. And if I run the simulation again, probably it will run it without power. Okay, it is recompiling the Verilog A models. Okay, and it is completed. All right. So then let me set the parameters again. This one, T, number of FFT, moving clock, settling time, edit. Eight, 0, sample, F4, 90 kilohertz, 1 megahertz, and number of real points here. Let me copy this and paste into here as a coherent sampling. Okay, then let me run it. Let's see what happens. Okay, so if I this, then first thing I want to highlight is input and output. Okay, and the clock bar. Those three things. Of course, the output here, output means output of the sampler. Okay, so for the clock bar, you can see that it has a track period, and hold period. And within hold period, we want to do the quantization. So we want to set as a clock bar here within the hold period. So when a hold is set, then we want to run quantization with 25% the period of delay. And for plotting those digital signals, you can either use this way. Yeah. So for this one, you can see that it is a kind of switching, right? For each binary signals are switching here and there, here and there. But for making this one as a bus, you first need to do is that this MSB, most significant bit, MSB, most significant bit, should locate on top, such that if you just drag it like this, then we cannot guarantee, the D7 is placed on top as the first one. So either you can do like manually moving one by one, moving signals one by one this way, or you can plot one by one in this reverse order. This way. So let me show how to make this one as a digital bus. So first you can select all of them and go measurement and analog to digital. So here, center voltage is half VDD 0.5 make bus. Make bus name is, let's say, 8-bit 7. So if you just click OK, then you can see that it is represented as a bus notation, as we have seen in our lecture slide. And this one is a binary representation. So if you go to radix and unsigned decimal, then you can see that its value is changing over time, right? And those values are, if you zoom in, then you can see that those values are updated at 25% later than the leading edge of clock bar signal, as we intended, as we set as a T delay as a 25% clock period. So this is not, intuitive to analyze whether these digital values are correct or not. So for that purpose, maybe I can set it very slow signal, for example, like 10 kilohertz. How about this one? And let's run the simulation again. 10 kilohertz. Right. Then, if you just press Ctrl R, refresh, then you can see that it is kind of shown as a slowly moving signal. But that you can see that for the input of the ADC, ideal ADC is low value, then of course it should indicate 0 and 1, 3, 1, 3, 5, 7, 10, and so on and so forth, going up and up and up, and then touching the maximum value to 55, like this way. And then if you click V out, then you can see that it's digital signal, and digital to analog converted signal quite nicely follows our sample and hold it analog to digital converted signal, and the input signal. Okay, so let me move back to our previous data, which is coherently sampled input frequency. Here, paste. Okay, let's run the simulation again. So for this, our design target is ENOB higher than 7.9 bit. Okay, if I refresh it, then definitely you can see this way. But what you need to do is running FFT of this V out. So go to measurement spectrum, and so for start point, the settle, and for the stop point, the friend, and topic 6. Click S, then you can see the half half Nyquist frequency, which is half of sampling frequency is set. And then you can see that if I set as a set t set 2 as 0 second, then indeed its value is actually sampling this one. And then let me see. So in this case, we are sampling with 1 megahertz, which is 1 second period. Okay, so V out values are updated with 25% delay. So what I'm checking is that we get sample here, and 1 second later, which is 1 period of our clock, then we are getting this sample. And for 2 seconds, which is twice of the period of the clock, then we get this sample. And yeah, for here, we get this sample because we set as a sampling frequency as a 1 megahertz, which means that 1 over 1 microsecond. So from this settle, as we set as a 0 second, we are getting samples 1 megahertz clock period later, and we get next sample, and so on and so forth. So FFT runs this way within our CAD virtual environment. And then if you just click the FFT units here, plot it, then you can see that its ENOB value is 7.9 bits. This is quite obvious because, so we used IDER ADC, and we also used IDER DAC. So what we are seeing is that the linearity or ENOB of, the linearity because of bootstrapped sampling switch. So distortion, let's say distortion or non-linearity plus quantization noise is transferred into V out, and we are looking at that one as a form of FFT. So that's the purpose of our simulation setup. In contrast, for example, if I try to plot this one, then definitely we can see this kind of waveform. Is that if I do spectrum, and that's exactly same setup. And let me see for this one. Yes, so we are indeed sampling the voltage here, 1 microsecond, 2 microsecond. But this is a bit it's not stably set, because in the vicinity near here, 1 microsecond, it switches suddenly from here to there. So it may be getting the sample in the middle of switching here or maybe here. So it is a slowing switching in this way. But what I mean is that it will be better or safer to set some delay, more delay. So let's say get T settle. So for example, 7.5 over clock. Then let's see what happens. Okay. I refresh it. Okay, we can refresh it. And then we open this spectrum. Click S again and plot it. Okay, then you can see that its non-linearity is plotted this way. So I just change it this settle time, right? T settle here as a 75% clock, such that its FFT range is actually from here till the end of the stop time, which is T trend. Then we can make sure we are getting samples at this point only, not in the how do I say, in indefinite range, or for example whether here or here. So you can see that obviously its distortion level is far lower than the quantization noise. So this one, the green curve is the point here at the output of sampler, and the red dot, the red curve here, red curve is here, which is ADC plus DAC. So red one, it includes distortion plus quantization noise. And for the green one, it includes distortion only, right? So if we can set distortion far below, down to much lower than the quantization noise, then its ENOB should be set as close as possible to 8-bit, right? So here it says 11-bit, which is just it doesn't make sense to that much. The sampler itself can guarantee very high linearity, or in terms of effective number of bits. So we verified that it is higher than 7.9 bits in our lead curve. This one is the data about green curve, so we can just close it. And let me move on to the next step. So ENOB degradation with thermal noise. So now we are testing our Verilog A model's noise. So for the intention of this part is that what will happen. So here we have added the nonlinearity, which is distortion of our sampler. But as we studied in lectures, there can be amplifier, or there can be some buffer, or there can be some filter. Sorry, in this case, filter, maybe you can draw it this way, filter, amplifier, or buffer, or maybe amplifier, another amplifier can be added here. Then every single circuit will have or may have the noise. Then we have to somehow model the preceding stages noise values. For that purpose, we can use our Verilog A modeled noise. Let me see. Let me go here, make editable. Okay. So here we can place our noise source as we used in previous video. And for here, I guess it's AHDL lib and adder. Then you don't need to worry about setting K1, K2 values. You can just put it here. And noise, or this way. Okay. For input here. This way. So what is happening is that we are intentionally or adding on purpose of noise input. So this one is just an adder, kind of signal in 1 plus signal in 2 is this node. Okay. So using this noise, then for an 8-bit ADC with full scale 1 volt and for example frequency 1 megahertz, you can calculate the quantization step, which is quantization step as you studied 2 to the power of, for example, 8 ADC. Oh, no, sorry, it should be the other way around. 1 volt. Then this one is delta. And for the RMS noise, Q RMS, which is, if I remember correctly, then it goes to delta over square root 12. Then this one is the RMS quantization noise, right? And then this one is spread out in frequency domain, and fs over 2, which is Nyquist frequency. Those are spread out as a uniform distribution, white noise, not modeled noise. That means this one is a RMS noise, and if this one is spread out uniformly over a frequency domain, then what will be the noise density? Not the RMS, but this one you can call power spectral density. Density means 1 hertz. Okay, let me use different notation. 1 hertz normalized here per square root hertz. For this one, then because RMS noise is delta over square root 2, then its power, the power for the entire frequency domain, the summation value of the power is this square, delta square over 12. Then this one is spread out over entire fs over 2 bandwidth. That means if you multiply fs 1 over fs over 2, then we get power domain voltage power spectral density, which is voltage square over hertz. And if you apply square root, then you can calculate the quantization noise density in terms of voltage per square root hertz. Then maybe we can use a built-in calculator in impedance virtuoso, power of -8. Yeah, then it is done. We divide square root 12. Then yeah, it is indeed 1.13 millivolt, which is e to the power -3. And then, okay, it works. Then if I divide this one by the 500 kilohertz, which is fs over 2, then let me see. This one should be divided by delta over square root 12. If we divide this one by square root fs over 2, then we get voltage per square root hertz dimension. For this, we can apply this way. Then if I calculate, then it says it's failed. Let me see what is wrong with this. Not sure. Okay, then we can see that approximately to 1.6 microvolt per square root hertz is the quantization noise or power spectral density. And this one aligns to the pre-calculated value as I did before I this CAD exercise. So for the bandwidth, we can set as a 500 kilohertz, which is Nyquist frequency, and 1.6 6. Yeah, so then we can run simulation. Yeah, then we have set a better log A noise plus input that goes to sampling switch, and that goes to either ADC or either DAC. Okay. And then if I plot this one, let me close this one, and then if I plot the noise, it looks like this way, and go to calculator, RMS. Then let me see, it goes to 900 microvolt, which is very close to 1.13 millivolt, but still not good enough. Try this way. Okay, but you press it and go to calculator and RMS. Then 1.3 is slightly deviating from this value, which is 1.13, but still is pretty good approximation to this RMS noise and our additive noise value. Okay, then we can now plot this V out, and if you go to spectrum, it's quite laggy. So for instance, if we set it as settle and trend, and we have run it as 2 to the power of 8 and 2 bit 6. Okay, before we go there, and let me double check such that our T settle is 750 nanosec. Then 750 nanosec is here, which should not be this way. In this case, we can just simply set as a 0. In this case, let's set T settle. Okay. So basically, I want to avoid to set as a start time, which is exactly overlapping this, the updating window, which has some uncertainty. Anyway, if I plot it, then yeah, it looks like weird, but we can control the range. For example, the minimum is not kilo dB, but let's say 100, minus 100 dB, and the maximum is just about 0 dB. Okay. Then you can see that is ENOB is decreased, right? From 7.9 to 7.2. So its difference is 0.7 bit. And Yeah, so our expectation is this. So if we add quantization noise, RMS, if we add random noise, which has RMS value exactly same as the quantization noise, then what happens is that for the SNR, then it is defined as the ratio of power of input and power of noise. For SNDR, then P in, P noise plus P distortion. Then this P noise, which is power of the noise, it includes quantization noise and other noise sources, for example, thermal noise and flicker noise and so on and so forth. So this part we modeled as a Verilog noise. Then if we make sure this additive noise is same as quantization noise, and if we can assume this distortion level is quite far below our quantization noise level, which is our case, right? Sampler case. Then is SNDR was this, but it is changed to SNDR PN plus PN, PIN, right? Because we added quantization noise plus another Verilog noise, which is exactly same as RMS value of the quantization noise. Of course, our RMS value is 1.3, but we will go through again. But anyway, let's assume that this one is same as 1.13 millivolt RMS. Then what happens is that its value is reduced. Let's use this notation, reduced by 2, which is 3 dB lower in power domain. In magnitude domain, is a 6 dB lower. Anyway, this is reduced by the factor of 2, right? So factor of 2, when we convert back to our linear domain, which is our bit case, which is that is 0.5, right? 0.5. If we add another noise that has exactly same as quantization noise RMS value, then our effective number of bit ENOB, which is defined as SNDR minus 1.76, which is divided by 6.02. This represents the factor of half. Then we expect ENOB will be reduced by 0.5. This is our expectation. Of course, it is reduced by 0.7, right? That is because we added more noise than the RMS value of quantization noise. Let me plot our noise here. Okay. Okay. This is our noise, and if we go calculator and RMS, then it's a 1.3. So our Verilog A based noise modeling, this is not perfectly modeling as exactly same as we expect to. So for example, if we want to reduce this one such that it can become to like 1.13 to power 3. And let me calculate what is the ratio. 0.857. And this one should 0.85 should be factor of the new bandwidth, the previous bandwidth. And if I multiply this one by square, no, this way. Okay, 7.3. And apply this way, 7.3, and see what happens. Okay, if I refresh it and calculate RMS again, there is a quite closer. Of course, there is a still deviation, but it's quite closer to 1.1. And let me see if I run the spectrum again, then let's see what happens. So now it is increased to 7.5. So previously, our ENOB value was 7.9. So its difference is reduced, right? Only 0.4, of course, because we added this much of noise. If we add more, higher number of RMS value, then it will be much closer to 0.5. But I would say this is quite closer enough to our theoretical expectation. Okay, then the last step as a bonus point was sweeping the noise, plot ENOB versus noise density. So for that one, I have prepared a Python script. Here, code. All right. So our ENOB value is defined as SNDR minus 1.76 over 6.02. And then SNDR, if we apply the noise, additive noise, then SNDR is defined as power domain. Then we first take the ratio of signal power and noise. So this one, for the sake of simplicity, this one is power of noise plus distortion. So I just note it as a N, D. And then if we add noise density, then we first need to convert this one as a power domain and times with the bandwidth, which is fs over 2, which is spread out over over our Nyquist band. Of course, we didn't apply this one exactly same as Nyquist band, but this one is a Verilog A modeled noise, which is sometimes not exactly modeling theoretical expectation. So if we plot this, then you can find is relationship such that as we add more noise, which means that preceding stage has higher noise before we do ADC quantization, then its ENOB is reducing from here to there. And of course, to get this kind of plot, you can just run parametric analysis and go to, it should first set noise here and go to log A and assign this one as ND. ND. And it was previously set as 1.6 microvolt. Then if we, do the parametric sweep, for example, from 100 nanovolt to 10 microvolt, I'm just randomly choosing the numbers, and total step will be 10 or 20. Then it will take a lot of simulation time, but you will get, in the end, similar data as I previously have run the simulation. And when you plot it, then you can see this kind of plot, similar to this kind of plot simulated ENOB and theoretical ENOB. There is some discrepancy, I would say, but still it follows quite well with our theoretical expectation. And you can use this kind of Verilog A-based modeling method to your ADC design and theoretical verification. Okay, this is the end of our CAD exercise video recording. Thank you for your watching, and I hope these videos can be helpful for your practical analog circuit design and ADC design, whatever circuits you are designing for. Thank you.